This gentleman's latest book is called The Great Paradox of Science, Why Its Conclusions Can Be Relied Upon Even Though They Cannot Be Proven. That's why I did that effect. This is a world we live in where we don't know what's fact and what's fiction anymore, and it's up to people like us to try and just take the right fork in the road and totally confuse people. No, I'm only kidding. We want to provide theories that work without necessarily being true. I suppose you could say that. So I'm gonna read from his notes here real quick. And you got the little thingy ready, okay? So Mano Singham is a theoretical nuclear physicist who worked for the last 30 years at Case Western University in Cleveland, Ohio. He is the author of 4 books. His third book was God versus Darwin, The War Between Evolution and Creationism in the Classroom. His latest book is The Great Paradox of Science, released by Oxford University Press, a very good imprint, if I may say so. He's a fellow of the American Physical Society. This book happens to be for sale, just like my book, which I'll talk about maybe at some point. $30 at the table here, hardcover, Oxford University Press. Get it. Okay, here he is, ladies and gentlemen, Mano Singham. Thank you, sir. Very nice to open for you there. Thank you very much. My pleasure. Let me get out of here.
Thank you, Mark. Thank you, Susan, for inviting me for this program. My publisher asked me to plug the book whenever I get the chance. So I apologize. This will not be the only plug for the book. But anyway, so the book is called The Great Paradox of Science. Now the subtitle, Why Its Theories Work So Well Without Being True, was my original subtitle. And the publishers and editors liked the book, but they were nervous about the subtitle, especially the word true. Because as you know, the enemies of science, the people who seek to discredit science, are very good at what's called quote mining. They take things out of context, out of scientific literature, and use it in a way that was opposite to what the speaker intended, or the writer. Darwin suffered from this enormously, because Darwin would always set up his book, it's very hard to imagine how this could come about in natural processes. And then the rest of it was explaining how exactly it came about in natural processes. But the critics would take that first part and say, see, even Darwin said that this was impossible to explain with natural processes. So the publishers were nervous that the critics of science would take the word not being true and use it out of context. So they made the decision, and in consultation with me, why its conclusions can be relied upon even though they cannot be proven. So the word true doesn't appear there. But I like the original subtitle. I think it gets my point across better. Many of the things that I've been talking about today will be to dispel very, very common misconceptions about science and the nature of science. And these misconceptions are held widely within the scientific community and also in the general public. So how can I so confidently assert that what is so widely believed are misconceptions? Well, one possibility is that I'm some kind of crank who managed to weasel his way into this place and give this talk. And you must always, as being skeptics, you must always keep that as a possibility. But much of what I say is not controversial among the historians and the philosophers and sociologists of science. Much of it is common knowledge, but it hasn't percolated into the other communities. Why is that? Well, one reason is that the conclusions of the philosophers and sociologists and historians of science, that we cannot really sustain the belief that science is heading towards the truth, is unpalatable to scientists, because I'm a member of the scientific community, we strongly grew up with the belief that we are searching for the truth and that we will find it. So the conclusions of these other academic disciplines were not congenial, and in fact sometimes have become very hostile. Scientists have been very dismissive of the work of these people because those people haven't been able to sustain the scientists' own belief that their work is heading towards the truth. And it has erupted in things called the science wars, some of you may be familiar with. The other reason is that much of the beliefs in the popular community, scientists, when they go through their period of training, going through the PhD and so on, like me, we are never exposed to the work of the philosophers, historians, and philosophers of science. What we get is folklore that's passed from scientists to their students, to their students, to their students, and perpetuates itself. And because we hear it from the entire scientific community, we think it's true. We think that this is how it truly is. And it is the scientists who write books popularizing science to the general public. So that's how those views have come into the general public. Philosophers, historians, and sociologists of science, they write books too, but if you read them, you will find that they are less accessible. They're written in a sort of style and jargon that makes them hard to assimilate. So they haven't really caught on, except for one or two. So that's my prologue to explain why it is that many of the things I'm going to say today will be controversial to perhaps many of you, but it is not controversial to the people who actually study the nature of science. Okay, it's easy to take science for granted, the success of science, and this cartoon is a good example of that, of a politician who's ranting about, you probably find members of Congress today like that, who say things, what has science ever done for us? And they forget that pretty much everything in their lives is a product of science. I love the one where it says he's alive 50 years past his expiration. Okay, if you can see it at the back. It's also, some of you may remember the film Monty Python's Life of Brian.
Yeah.
Should have won an Oscar, but never did.
Yeah, sure.
But, do you remember the scene where the leader of the Judean People's Front, Reg, played by John Cleese, is trying to incite his followers to revolt against the Roman occupiers. And he says, what, apart from the aqueducts, sanitation, roads, irrigation, medicine, education, wine, public baths, freshwater system, law and order, public safety and peace, have the Romans ever done for us? And that's pretty much a similar sentiment. It's easy to take things that we are used to for granted and not realize where they came from. And that's true with science too. So first question, what is science? You would think that given how important science is, it would be easy to demarcate science from non-science. Turns out that it's not. True demarcation criteria require what are called necessary and sufficient conditions. But no satisfactory conditions, both sets of conditions have been found. We do have necessary conditions, which says that all scientific theories should be naturalistic. That is, there should be no appeals to the supernatural, and they should be testable. That is, they must make new predictions that can be observed or experimented. Those are two conditions. Miracles do not belong in science, the naturalistic condition. This is a very famous cartoon from Sidney Harris, where there is a long proof, and in the middle it says, then a miracle occurs, and the senior scientist is telling the other guy, I think you should be a little more explicit in step 2. And that's true. We don't allow miracles in science. The evolutionary biologist Richard Leverkin says, you cannot allow miracles in science, because if you allow even one, there is no limit. There's nothing you cannot assign to miracles if you allow even one. So what about this thing that we call the scientific method? And some of you who have children who go through science fairs, have to take part in science fairs, they're given this list. This is the scientific method. You see it all the time. And here's the posing a question, conducting research, conducting a hypothesis, conducting experiments to test the hypothesis, and then analyzing the data, drawing conclusions, and communicating the results in the form of a scientific paper. And we are told that this is the scientific method, and some would argue that it is the scientific method that makes science what it is. But that is not how scientists actually work. Okay? How scientists actually work, they do use all those things, but not in any prescribed order. Usually, scientists are just messing around, most of the time. They jump around from the various things, and they use heuristic methods, meaning intuitive gut feeling methods to decide what's the best thing to do at this time. Should I try a new hypothesis? Should I do a test? Should I do some more background research? Should I do this? They jump around, and to the untrained observer, it may look like they're just messing around. But there is a kind of reasoning that goes behind it, but it's not in that order. It's only when the research is done and they are ready to publish it that they go back and write it in this order. There's a lot of rewriting, historical rewriting in science, and this is important to realize. So, science works exceedingly well. That is unquestionable. I think nobody will deny that. And it seems to show continuous progress. It's getting better all the time. Now, it seems plausible that that could work so well because its theories are either true, that is, they are accurate representations of the reality of nature, or they are steadily approaching that reality. Right? But neither belief holds up under scrutiny. Philosophers and the historians and sociologists of science have looked very hard and find that there is no reason to think that scientific theories that we have are true or getting closer to the truth. And this is one reason why scientists hate these philosophers. I'm not kidding. There have been some really vitriolic articles written by scientists just condemning these entire fields, and I think that's unfortunate. And part of my reason for writing this book is I actually stumbled into this area while doing physics. I got interested in the history and philosophy of science, and I found that what these latter groups were saying was very important. So I wrote this book as a scientist to try to get the scientific community and the general public better understand what these philosophers and historians and sociologists of science are saying. That was a goal, because they're saying important things that the general public should know, because by knowing them, I feel we can defend science better from its critics than the superficial folkloric knowledge of science that the scientific community possesses and which they are passed on to the general public. We need better defenses, and that's what's going on. Common beliefs about science. Scientific theories make predictions. Experiments test those predictions. If the experimental results agree with the theoretical predictions, the theory is confirmed or becomes more probably true. If the experimental results disagree with the theoretical prediction, the theory is falsified. Fred was talking about falsification. Sorry, Fred. I'm going to argue that falsification is no good. Okay? I hate to contradict the previous speaker. Popper made a very important contribution to falsification. And as Fred pointed out, it gives a nice, simple model of science. But it turns out, and this is why a lot of scientists, when they talk of what science is, they talk of falsification. Because falsification seems to provide a good rationale for what they do. But after Popper, people came along and looked at it and found that falsification simply does not hold up under scrutiny. It's a long argument, and I wrote a 300-page book, and I'm not going to be able to summarize everything in 20 minutes or 25 minutes. But trust me, this is the whole point of this. We have to go beyond falsification to get a better understanding of science. So why does falsification not work? So things are not so straightforward. Because if you look at what a theoretical prediction is, it's a package made up of 4 components. The basic theory or theory, say the Newton's theory, or Einstein's special theory of relativity, or the general theory of relativity, or whatever. There's a core theory or theories. But you also need things called initial conditions. How did the system start? What are the assumptions about how it began? You can never apply a theory straightforwardly. You need other auxiliary assumptions. You need simplifying assumptions to make it workable. You know, the famous example, how would a theoretical physicist describe a cow? Well, he said, let's start with a sphere. Okay? That's what a cow is, as a zeroth order approximation. So you need simplifying assumptions because the reality is much too complicated to deal with directly. And then there are other clauses that we put in saying that we assume that all other things being equal. In other words, apart from, we are assuming that everything else that we have ignored does not play a role. So there are four basic components to a theoretical prediction. How about experiments? Well, when you do an experiment, what you get is the raw data, which could be a reading on a meter, clicks in some Geiger counter, bubble chamber tracks, or something. Those are the raw data, but those are just meaningless things. Those are just meaningless sensory data. To convert them into concepts, you need interpretive theories. If you take a meter, say a voltmeter, it gives you a needle that points to say, how do you know that's 6 volts? Well, you need a theory of how the voltmeters work. That involves electromagnetic theory, mechanics, all kinds of other theories. So to convert that needle to a voltage requires a lot of theoretical work. Then there's also, unproblematic background knowledge. That is all the other theories used to extract information from the raw data. We assume that all those other things don't matter. Okay? So basically, we can only compare the theoretical prediction package with the experimental result package. And if they agree, then all we can say is that we have consistency among all those 7 elements, that they're all working together satisfactorily. But if they disagree, we cannot say the theory is falsified, since the problems or the reason for the disagreement could lie somewhere else in that package. And this is why falsification doesn't work. You can never say it is the theory that is falsified, but it could lie somewhere else. In fact, I would estimate that about 90 to 95% of science consists of people looking at all those other factors to see where the problem lies. When you get a disagreement with, say, Newton's law, people don't immediately say, Newton's laws are falsified. We never do that. It's too valuable a theory. We look to say something must be wrong somewhere else. And people look very hard, and most of the time, that's what happens. And they find it. Okay? So, as a result, this is a key slide. Science cannot prove theories to be true. Science also cannot prove theories to be false. And that's the big thing that people have trouble getting over. All scientific theories are underdetermined by data. However much data you collect, you can never uniquely pinpoint and say, that points to this theory. There are always alternative possibilities. Scientific facts are not unchanging objective statements about nature, but are theory-dependent judgments. For example, I read that chapter in the book about the age of the Earth, how the age of the Earth changed from millions of years to 6,000 years, to then hundreds of millions of years, then 10 million years, and now to the billions of years. And this was going to be my original talk that I was going to tell Susan. But basically it changed because the theories used to arrive at those conclusions changed. So facts are theory-dependent judgments. So the central question, if the comparison between theoretical predictions and experimental data can neither confirm nor falsify theories, why bother to do them at all? What purpose do they serve? But they serve a very important purpose. It's the result of these comparisons that what constitutes evidence in science. What we call evidence in science are the results of those comparisons. It is this evidence that is used in evaluating the merits of theories. How scientists work? Scientists use heuristic methods that consist largely of trying out theories and revising them on the basis of evidence. That is one of Popper's very important insights. Don't get me wrong, when I say Popper's theory of falsification doesn't work, that does not undermine the fact that he was one of the giants of the philosophy of science. He contributed a lot of immense things. falsification, unfortunately, it doesn't hold up, but a lot of the things they do. The philosopher of science, Pierre Duhem, made the important point that individual scientists act more like physicians than watchmakers. Now, what did he mean by that? So, if you go to a watchmaker with a faulty watch, she can take apart the watch into each component, take this component, test it, and see whether it works. If it works, leave it. Take another component, test it, and see if it works. Each component can be tested separately, and until the faulty component is found and replaced. But a physician, if you go to a physician with a problem and he says, I think the problem is the heart, you can't take the heart out and test it. You can't take the liver out and test it. You have to test it even while it's connected to everything else in the body. And scientific theories are like that. No individual theory can be tested in isolation, because all the scientific theories are connected to other scientific theories. So you have to try and understand them in situ. Okay? So, but the scientific community works like a panel of judges, weighing the evidence and arriving at a consensus verdict on which theories or paradigms to accept and which to reject. The philosopher of science, Barry Barnes, said, because of this, paradigms are always provisional. Well, it means a paradigm, I mean, it's a synonym for scientific theories. In agreeing upon a paradigm, scientists do not accept a finished product. Rather, they try to accept a basis to future work and to treat as illusory or eliminable all its apparent inadequacies and defects. In science, there is no basis for validation superior to the collective contingent judgment of the paradigm-sharing community itself. So in science, what is true is what the scientific community, the credible experts in that field, say is true. That's the way it is. Now, there's something called scientific logic. And that's important, because that's how scientists use, what scientists use to make judgments about truth or falsity in theories. But scientific logic can be used and should be used in everyday life as well. In fact, very often we use it without being explicitly aware that we are using it. And part of the goal of the book was to make that implicit understanding explicit. One piece of scientific logic is that existence claims for any entity, if you claim something exists, those claims are presumed to be false unless there is a preponderance of evidence in favor or its existence is necessary as an explanatory concept. The reason we don't believe in fairies or zombies or unicorns is because A, there's no preponderance of evidence in its favor, and 2, we don't really need them to explain anything. So why do we have them? Now, there were things like the ether, some of you know. There was no positive evidence for its existence. In fact, it was very elusive. But it was necessary as an explanatory concept. We needed at one time to explain it, to explain how light travels through empty space. So we gave it provisional existence status. We said, okay, we need it, we believe it exists because we need it. But once Einstein's theory of special relativity came along, he didn't prove that the ether didn't exist, as many people saw. He just made it unnecessary. So it was no longer an explanatory concept, so we threw it out. And a lot of scientific things that phlogiston was a theory of combustion, was a dominant theory of combustion, and it was introduced as an explanatory concept. But when the oxygen theory of combustion came along, it became unnecessary, and now phlogiston no longer exists. We didn't prove that it didn't exist. It was no longer assumed to exist because there was no positive evidence in its favor, and it was no longer an explanatory concept. Universal claims, on the other hand, are presumed to be true unless there is a preponderance of evidence in favor of an existing claim that contradicts it. Scientific laws are universal claims. When we say energy is conserved, the law of conservation of energy, it's a universal claim. We're saying it's true for everything. When we say all electrons are identical in mass and charge, that's a universal claim. We cannot possibly prove it to be true. How can we test every electron in the universe? We can't. But we assume it's true unless somebody can come along and show me an electron or something like it that has properties that contradict it. And negative evidence like that, universal claims, That's how we believe the scientific laws. Not because we have proved them to be true, but because no contradictory evidence has been found. So negative evidence plays a critical role. I won't go into this because I'm running out of time. How science progresses. New evidence, positive and negative, is constantly being generated and evaluated. The scientific consensus verdicts can shift from one paradigm to another based on new evidence. That's why we get scientific reversals. Not because the theory has been falsified or otherwise. It's because new evidence keeps coming along and the scientific community makes a judgment that the new evidence favors this paradigm over the old one. Okay? After a paradigm shift, history is rewritten so that this is always seen as progress, just like the political revolutions. When you have a political revolution, the victorious side gets to write the history. And they always write that the revolution was a good thing, because they were the winners. And the same thing happened in science. Okay? Now, I'm not sure why that thing is black. It shouldn't be black. It should be like the others. But this is an example of how paradigms change. And being black is going to be a bit of a problem. I'm not sure what happened in the transition. But basically, this is paradigm A. It's like a hairpin, like this. Everything should be like this, okay? Forget the black shading. It should be all like this. Paradigm A, all this area inside is the region where paradigm A agrees with the data. Now, outside here, there might be something that doesn't agree with the data. Now, if something doesn't agree with the data, scientists working within paradigm A will do two things. Theorists will try to make the arms of the thing wider to encompass the data point, whereas experimentalists will try to make the data point come within paradigm A. Most science is like that. But there may be a data point outside that's inside the region of paradigm B that cannot be brought into paradigm A. At which point this becomes kind of a crisis. And that's when people start looking for alternative paradigms. And so paradigm B might come along that explains this new point. As an example, paradigm A could be Newtonian mechanics. The anomalous data point could be the perihelion of Mercury. People tried for over 100 years to try and explain it. Couldn't. But then Einstein's general theory of relativity came along and found that it could explain them. Now, Einstein's general theory of relativity didn't explain a lot of other things that Newtonian things had explained, but it explained this big troublesome point. But it also went further. It found it predicted a new thing, the bending of light from the sun, which Newtonian theory hadn't predicted. And when experimentalists found that gave a huge boost to paradigm B. It's like a surprising novel prediction that Popper mentioned. So scientists decided paradigm B is what we think is true. So they went to paradigm B. But subsequently it might happen again, a similar process to go to paradigm C, and then to paradigm D, and so on. That's how paradigms change. But note that the anomalous behavior that signaled the shift from A to B was not unique. There could have been an anomalous data point somewhere else in a different direction, which people hadn't noticed at that time. And if they had noticed it and worked on it, the shift might have gone from paradigm A to paradigm B, P, and then to Q and R. There could have been an entirely different evolution of science, ending up in a different place. Okay? It's like the tree of life. This is Darwin's evolutionary tree of life. He had only one figure in his book, Origin of Species, a tree like this. This is, frankly, a nicer figure. Using a fractal software program. He do it by hand. But basically, the tree of life says, you start out from a few organisms here, and then due to mutations and various things, they change. And the branches change and diverge and so on. And you end up with all the organisms that we have now. Now, the extinct species were those branches that ended up somewhere in the interior of the tree. Whereas the canopy of the tree consists of those species that currently exist. That's the tree of life. So, sorry, I should have come this. The progress, no, the tree of science is similar. It starts out from a few theories, then as it goes along, scientists make judgments as to which paradigm to choose, and they go along and you end up with all these various things. History of science. Depending on paradigm choices at any given time, you end up at various places. The point is, this process is historically contingent. How scientific paradigms change, like how evolution changes, is dependent on decisions made at any given context in history. And there are many factors, political, social, religious, cultural, that influence which paradigms succeed. If we could run the clock again, we believe that the living organisms that evolved would be nothing like what we have now. There's no reason to think that what we have now is unique. Similarly, there's no reason to think that scientific theories we have now are also unique. They could also be very different from what we have now. The scientific theories that we have now are historically contingent events. Okay? This is another tree of scientific paradigms where I try to show that you start out with some few theories in the older days and they become more and more complex. Here we have theories of physics, chemistry, and current theories of physics, whereas the old theories have died out in the interior of the tree. In fact, the analogy of the evolution of scientific ideas with evolution of biological systems is almost perfect. How can this process be compatible with science progressing, getting better all the time? What can science be progressing towards, if not towards the truth? The problem is that we think that being able to successfully predict and control events must be due to our theories being true. That is the connection that has led us astray. And we can blame Aristotle for that. Aristotle believed that scientific knowledge was true knowledge. And ever since then, that connection has stuck. The reason why science works consists of consensus judgments made by credible experts using comprehensive bodies of evidence that are systematically acquired, evaluated using scientific logic, and passed through institutional filters such as legitimate peer-reviewed publication. And here's the key question I want to leave with you. If extraterrestrials visited the Earth, they would clearly have a technology superior to us. After all, they have come here and we haven't gone there. But would they have the same scientific theories? If your answer is yes, then you believe that theories are universal and just lying about like fossils, waiting to be discovered. If the answer is no, then theories are inventions that are not unique, but are context and history dependent. My feeling is that the answer is no. The wealth of scholarly evidence is that the answer is no. We have no reason to believe that the theories we have are unique. It should be sufficient that science works so well, and that questions of truth are irrelevant and a distraction. Because all these, because once you start talking about truth, then the religious people say, well, we have the truth. I say, I don't care if you have the truth. Does your theory work at all? When they say, well, if science is not true, what's the point? I said, science may not be true, but it works really well. Your theories are not only not true, they don't work at all. Okay? And I think that's a far sounder defense of science than trying to debate which is true, which is a question which you cannot answer. At conclusion, this is from Thomas Kuhn, who's probably the most significant thinker in this area of philosophy of science. He says, can we not account for both science's existence and its success in terms of evolution of the community state of knowledge at any given time? Does it really help to imagine that there is some full, objective, true account of nature and that the proper measure of scientific achievement is the extent to which it brings us closer to that ultimate goal? Thank you.